I am Molly Copeland. I am a PhD student here at Duke in sociology, one of Jim's students, and I'll be talking about basic network description. The goal is to give kind of a conceptual overview because it's such a broad part of the field. There's so many different measures that you could have depending on what exactly you need. So my goal is to kind of help you figure out what you need and how to think about it in a way that you can tailor more to you. But of course, feel free to interrupt at any time with questions. So broadly, we're going to be going over centrality, different ways of thinking about connectivity and cohesion, so kind of broader patterns of structures within the network, and then a little bit about thinking about roles, since that helps to kind of lead into the next section when Peter will be talking about community detection and things like that. And again, it's not going to be exhaustive, so there will be a lot more than is going to be included in these slides, which the slides I think will be available at the end of the week as well. And then it's focused on concepts, so I'm not really going so much into the underlying math. I'll have a few formulas on the slides for you. When you do get the slides, there will be a lot of hidden slides that have a little more detail about the math. But since now we're mostly using statistical programs where it's doing all of that for you, and you're just kind of like pushing the betweenness button rather than calculating it yourself, I didn't want to spend a lot of time going into detail there. All right, so starting with centrality, just to give you an idea of where we're headed, going to talk about individual node characteristics, then look at sociocentric and egocentric networks, so kind of the corollaries on a more global network level, and then finally look at structural wholes. I want to point out that there are a lot of different ways you could kind of frame thinking about descriptives or even centrality. So you can think about descriptives on kind of a micro, meso, macro level, so things that make networks kind of at the micro level of connections between individual actors, things that generate subgroups within the network, things that describe the entire network overall. I'm taking a slightly different approach, which I hope is more intuitive to people that are coming from kind of a regression and attribute framework. So thinking about the characteristics of particular nodes or actors, then thinking about, well, what is the corollary of that if we're looking at an entire network? So if we have centrality for an individual actor, how would we measure centralization for a global network? And then thinking about kind of the in-between pieces, the larger structural patterns that we can have in terms of connectivity and cohesion. So starting with centrality, it would seem like a very simple question that you're probably interested in for a lot of questions in the health field. How would we distinguish an important actor? So who is important in the network? Who is an important stakeholder? Who is able to spread information? But that gets very complicated. Measuring the center is not easy, especially as your graph gets more complicated. So just a few toy examples that I'm going to kind of come back to throughout these slides. So distinguishing the important actor might be very easy if your graph is like this, right? There's kind of a clear hub in the middle of this star network here. But it's a little more complicated if you have something like this, or a chain, right? So knowing who is more important and in what way gets a little less intuitive if you have even these kind of toy graph examples. Or you might want to kind of choose between these two actors in the middle. So different centrality measures are going to indicate different kinds of importance in this vein. Okay. So we're going to talk about degrees, closeness, betweenness, and information and power. And just to reiterate that there are many more than these four types of measures. But before examining kind of each in turn, there's one more kind of conceptual step that I think it's important to think about in terms of what is actually flowing through the network. So what measure you want to use depends in part on what kind of process you're modeling. So you need to take a more theoretical step back to think about the ways that whatever you're modeling might actually move through the network, right? So if we have different kind of types of paths or walks through the network, so a path would be kind of a sequence with no edges or nodes repeated. Trails is where there's no edges repeated, and walks are a little more unrestricted, so ways that anything could kind of move through the network at any time. You could imagine different ways that different items or bits would kind of move through the network, right? So package delivery, if you have one package and it's moving sequentially kind of in the quickest way possible to a specific destination, that's going to be a very different type of process than gossip, where certain people are going to be particularly avoided, right? Or it might be spread in a different way. So these are kind of perhaps silly examples, right, compared to what you are including in your studies, but this typology of whether or not things would be flowing in kind of a particular direction, whether or not they would go back over a node that they've already traversed, right? So gossip might come back to somebody who's already heard it in a way that probably package delivery or even sharing a book in a book club wouldn't. So kind of that basic underlying conceptual process is very important when you're thinking about what centrality measures you want to choose. And this is from a paper by Borgatti in 2005 that looks at centrality. I also have a note of a slide of citations at the very end so that you can go back and find the original references. And I also included some of the references that I found particularly helpful that were geared towards explaining network descriptives, particularly for people in health and public health. So those are included as well. So. Oh, it's just highlighting my. All right, so thinking about centrality, you're probably all familiar with degrees or degree centrality. So this would be the number of ties that in any given node would have in the network. So here our hub has 7 ties, whereas the people on the outside have 1 tie. You can have undirected, which means there's no particular point to the tie. It's mutual by default. But of course, in addition to undirected, we might have directed ties where we'd be distinguishing between in degrees and out degrees. So if you were nominated as someone's friend versus if you are sending a nomination. And I study adolescence and mental health, so you're going to get a lot of adolescent friendship examples. So kind of apologies in advance. This is actually one of the networks that you're going to be creating later in the lab with John. And it's a bit fuzzy here because I tried to expand it and squeeze it into the slide with this text, but you could see that certain nodes have lines with arrows pointing that they nominated someone else as a friend, right? And if you're thinking about perhaps more complex processes like disease transmission, that it might be important to have kind of the direction of the spread, right? Isolates were people with 0 ties or nodes with 0 ties if your nodes aren't necessarily people. They can be a special case because they are not connected to the network. So if we're measuring other processes like closeness, like distance across the network, what is a distance for somebody who's not connected, right? So that kind of brings up some problems later on, or some ways that you have to think a little more carefully about isolates because they might be excluded from some of the typical network flow processes. And that could be protective, right, if we're talking about something like disease transmission, but there also might be risks with that as well. So we might be a little more concerned about the mental health of students who have no friends in their school or things like that. Okay. So just to give an example, this is from a health paper by Cornioko and co-authors where they're testing salivary cortisol in nursing school students. And they do a kind of a friendship nomination process, and cortisol would indicate stress. So just to give you an idea of somebody who is using degrees in a kind of current paper, a current health paper. So this is the network, and the nodes, I think, are sized by their gregariousness, so their in degrees and out degrees. And they actually find a distinction between in degrees and out degrees and ego network density in terms of stress. So individuals who were not sending as many ties into their group, who didn't have friends within their group, what they characterized as low gregariousness, so low out degrees, actually had higher levels of cortisol, indicating higher stress. And there was kind of a curvilinear effect for in degrees, for what would typically be popularity. So the people with kind of middling or average popularity had much lower cortisol, whereas the people who were very popular or not so popular had higher cortisol levels for stress. And that's a fairly typical finding, to find that there is not only stress associated with in degrees and out degrees, but associated differentially with different kinds of in degrees and out degrees, and this kind of curvilinear pattern, particularly for popularity, when we're looking at things like friendship. Does anybody have any questions or any concerns with being able to see the screen, anything like that? We good to go? All right, great. But degree centrality is purely local, so it can be somewhat misleading. It can be kind of deceiving, and it might not be appropriate if you have non-local questions. So for example, you have somebody like this person with 5 degrees in this particular cluster who might look very important, right? Having high degrees, having high, perhaps popularity if we have in degrees and out degrees distinguished, or depending on whatever your nomination processes, whatever your edges are representing. But we might be more interested in kind of the position that this person takes, right? We might think they have a pivotal position in kind of connecting different clusters of the network. So we might want more measures than something that is purely local, particularly if you're collecting kind of larger structural global network data, right? If you're going beyond just ego networks, we might be interested in other measures that might be better for questions that are broader than simply the local level. So in that vein, closeness thinks about centrality as an actor is important or central if they're close to all other actors in the network in terms of distance. Right, so being able to reach other actors in the network, distance is typically considered as geodesic distance, so the shortest path between two actors, right? So yes, okay, so you've got the formula here. It's kind of the inverse of the distance when we're typically thinking about it in sociology. There you go, inverse of the distance between actors to each other. And one important thing that we're going to kind of circle back to is that every actor who is connected by at least one path would form a component in the network, right? So you can look at closeness just within components if your entire network is not connected. So we typically normalize this by graph size so that it ranges between 1 and 0, just to be kind of more intuitive, particularly if you're going to be comparing across graphs of different size. Yeah?
So that is inverse sum of distances, not sum of inverses.
Yes. Closeness also has a lot of particular different ways that can be measured. I know I have hidden slides about that as well, and that go through the matrix algebra and the graph theory. So that will be in the slides. Okay. Oh, sorry. And the question was the sum of inverses or the inverse of the sum. And I think we'd have the inverse of the sum. So because closeness is considering the sum and kind of the connections between every actor, you can only do it if actors are connected. So typically if you run closeness and you have isolates, you'll get something like infinity or not known or something like that. So you might want to look at closeness again just within the people who are connected, just within components. Yes?
I just want to clarify that this formula takes into account the network size. So how?
Yeah, so this formula is the one that's normalized, that takes into the network size into account. So G would be the number of nodes. So you're just kind of normalizing by size. This is the more derived formula that doesn't have that normalization. Okay. All right. So another warning for closeness centrality. Just like degrees, there's kind of a but here. And this is purely, you can just kind of see my graduate student frustration and tears in this slide, because this is a warning that in R, different programs like iGraph or StatNet are measuring closeness differently. So you're just putting in closeness, and if you're like me, you don't really go and stop and look at how they calculate it or what's under the hood. You're just assuming that it's closeness. So some packages, I think it's iGraph, which tends to come from from computer science, they measure closeness as kind of a distance or a cost for traveling that distance. So a high value is high distance, right? And a low value would mean low distance or cost, and you're very close. The social scientists tend to do it the opposite way. So high closeness means your nodes that are close, right? And low value on closeness would mean nodes that are not close, that are very far apart. So this is a particular warning that if you are interested in thinking about closeness, you need to be very careful about what you're measuring in this respect. Okay? And that would be true even if you're working outside of R. You want to double check your particular measure of closeness, because there are also several variations that have been developed over the years, and which way it kind of scales that measurement. Right. Moving on to betweenness. So this kind of gets to the idea of who are actors in important positions on kind of these connective paths? Who are the bridges in our network? So an actor is considered important if they control the information flow. So if they are on a path between other actors. So we count up the number of paths for a particular actor where they are on the shortest path, the geodesic, between two other actors. So thinking about this with our toy examples, for individual number 3 here, even though they have, or not individual 3, the person with 3 degrees in this position, even though their degrees might be lower than some of the people in the clusters, they would have very high betweenness because they're going to be on the path, the shortest path, the geodesic, between other actors. So this is kind of getting at that bridging aspect. It'll connect later to when we're talking about structural holes and kind of that, the idea of power or brokerage, right? Power to negotiate if you're connecting these different groups. So that might be very important if you're looking at something like disease transmission and you want to know how does it get between these separate clusters. Okay. Right. So again, we'd expect low betweenness for an actor who has very redundant ties. Or I guess they still have high betweenness. Information centrality, this is another measure that's similar to betweenness, but it's not just restricted to the geodesic. So looking at what can flow kind of through any path, not necessarily just the shortest path between actors. So actor J, who is on the paths between actors I and K, whether or not that's necessarily the shortest path. We'd expect things like information in particular to be able to flow in a lot of ways, even if it's not just the geodesic, right? Particularly depending on your nodes. So your actors might not think about the entire network structure when they're sharing information, and depending on what that information is, it might be shared as widely and broadly as possible. And of course, it wouldn't be sociology if we didn't have a 3x3 or a 2x2. So there's a lot of ways that you could think about these different centrality measures in combination and what that means practically and conceptually. Okay? So it's not very useful to talk about high betweenness or high closeness if you're not tying that back to some kind of conceptual measure, to some kind of meaningful idea within your network. So that's kind of the goal of thinking about things on this broad conceptual level. So if we come back to our toy examples, in the left graph, we would see relatively low degrees and high betweenness for one of our kind of connecting nodes here. So we might think about an individual with few ties, but they are crucial for kind of connecting the network or flow in the network. And then you might have something like the opposite, like in one of the clusters. So a lot of redundant ties. Right? Practically, you're not going to be working with toy examples very often, right? You're not going to sit down and be able to examine one tiny little cluster of your graph. So it becomes even more important, in my opinion, that you think about what the numbers mean when you're getting kind of the closeness or the betweenness for certain nodes turned out in your program. So finally, thinking about individual nodes, we might think about power. So it doesn't just matter that you are connected to other people, it matters who they are connected to. So who are the alters of your alters? Are you the king of the jocks or the king of the nerds in high school, right? You might have very, very different expectations for those students, right? So one way to measure this is Bonacic power centrality or Bonacic centrality, also called prestige. So measuring if you are tied to other important actors. So in this formula, the key difference with this formula is the beta parameter, which is kind of this tuning weight of how much should we count the centrality of the people you are tied to, or kind of how far out should we go in that network. So a larger value, you're giving more weight to the global structure. You're kind of saying that it's not just the friends of your friends, it's their friends and their friends, or whatever connections you might be having in your network. And a smaller value would just be looking at local structure. Okay, so as that beta parameter nears 0, we're just measuring degrees. Okay, so that's kind of something that can be tuned. You could also make it positive or negative, right? So if we might want to look at the high centrality of people who are connected to other highly connected people. We might want to look at high centrality of people who are tied to alters who are not central, right? So that might be important depending, again, on what you're modeling through your network. This is very similar to eigenvector centrality, which you might have seen before, but that doesn't have the beta parameter. Okay? And eigenvector, I think, can be very tricky in directed networks, if it works at all. So I know that for StatNet, they'll say, like, it runs it in a directed network, but what you get is not meaningful or kind of interpretable. So that's something to think about as well, that underlying structure of your network, whether or not all your ties are mutual, so it's undirected, or whether or not there is that direction, might change which of the centrality measures you want to use, right? And you can typically get directed versions, like directed centrality or things like that, or undirected, again, depending on your data. So just to give you an example of some of the values, and I know that's probably small to read the things in these tiny boxes in the back. I apologize, but it was very hard to fit everything on one graph and not have it completely look a mess. So if we have this positive beta parameter, right, our person who's connected to other important individuals here might have a Bonacic power centrality value of 1.14, whereas if it's a negative parameter, they're connected to other highly connected people, so that's 0.83, versus these individuals who are also connected to this unconnected person. They get a little bit of a boost here with a negative parameter compared to a positive. So just different ways you can tune that beta part of the equation. Okay, so that is just centrality when we're thinking about individual nodes, about who is an important person or individual in your network. Rather than just thinking about kind of important individual nodes, you might want to think about the characteristics of the overall network. Whether you're comparing between networks or just kind of characterizing this network, a lot of times comparing it to what you would expect at random, right? As we'll talk about in later sessions, I'm sure. So we're going to talk about kind of the corollaries of these individual centrality measures when we think about them in this whole network context. So degrees for individuals kind of correlates to the degree distribution for the entire network. So the frequency distribution of the degree values of actors. This can be particularly important if you are exploring network data for perhaps lesser known processes or kind of diffusion processes where you might be thinking about the degree distribution. So how many people have each degree value? How many people have 1 alter or 2 or 6 or 10? How many people have 0 friends, et cetera? This would be network size for ego networks. Okay. And you would also want to make sure you're thinking about constraints that might be imposed by your data collection methods. So if you have a cap, like in ad health, where you can only list so many other friends, that's going to affect your degree distribution. It's going to constrain what you observe. So you want to make sure that you're accounting for that in some way. Okay. Right. So this is a histogram from the Moritz and Kretschner 1995 classic where they're simulating sexual partners and the spread of HIV. So of course we have a spike for monogamy. A lot of people are just kind of having one sexual partner over the time that's observed. So considering monogamy in your degree distribution significantly affects what you would expect for the spread of HIV. Okay. So their results were that in 100 simulations, most only add 1 infected partner, the maximum is 16. So, and that's under 1% of the simulated populations. So it's not this kind of narrative of crazy HIV spread that you might expect from some kind of scale-free network because of the degree distribution having that monogamy kind of spike, right? We see this Poisson distribution. Or here it's not even necessarily. Centralization is the equivalent of centrality. So it's thinking about, or connects to centrality, it's not technically the equivalent. It's the extent to which centrality would be concentrated in a few actors versus more dispersed throughout the network. So how dispersed is centrality throughout the graph as a whole? And that would be particularly Freeman centralization. Again, there are a lot of small variations in how you would calculate that. So in our circle, we would have kind of this centralization of 0, right? We have a consistent no hierarchy, right? Consistent centrality versus much more centralization in our star graph. Density, you've probably heard of, so that is the the volume of relations in the network, so the number of ties that are observed compared to the number of possible ties, right? It tends to be quite low overall in our social networks, particularly if you have data that have been kind of constrained and how many people you can nominate, how many alters you might be naming, things like that. This is often seen as an important measure, though, for egocentric networks, for ego networks, right? So thinking about how many of your alters know each other and indicating the density of ego networks. So are your alters also connected to each other? Okay? And depending on, again, what process you're modeling, what your data looks like, you might be more interested in the density within the graph as a whole or across graphs, so components of the graph, things like that, right? So you could imagine how kind of the connections between people might be particularly important for different kinds of diffusion. So an example for this one comes from Fauci and McNeely in 2009. So they used the ad health data. So they're looking at friendships amongst adolescents. And they look at your ego network density, or what they call alter density, and ego network size and reciprocity. And they find that they're measuring depression as their outcome, they actually find a curvilinear relationship that varies for girls and boys. So there's a relationship between your ego network size and density. So girls were more likely to be depressed if they were in fragmented networks, when those networks were either very small or very large. Okay, so if their networks were not dense, they were kind of fragmented. Compared to boys were actually more likely to be depressed if their networks were very dense when they were small and large. Right? And we could think about how that might relate to different social processes, right? So different kinds of social pressures or influence or things like that based on the density of your networks and that combination, the interaction between density and size of your ego network. Okay. Any questions at this point? Great. Okay, so beyond centrality, beyond just thinking kind of the characteristics of the network or of important individuals at just the level of like what pieces are important, we might want to consider these more structural arrangements. And one way of thinking about that is in relation to alter characteristics. So homophily, of course, the tendency for actors with similar attributes to be more likely to be connected. And this translates to assortativity. So you might have assortative or disassortative mixing, right? So people who are similar being connected, but there are certain times where you might observe or expect dissimilarity to lead to connection, right? So if you're studying heterosexual partner networks, you're going to see disassortative mixing on gender, okay? Kind of by definition of your research question. You might see both. So again, in the adolescent networks world, we see assortative mixing based on not just homophily or personal attributes, things like gender, right? So you tend to have same gender friends, particularly in early adolescence. But you might see assortative mixing based on network features, like degrees. So popular kids might tend to be friends with other popular kids. But you also see disassortative mixing because the unpopular kids might be more likely to send friendship nominations to popular kids, kind of an aspirational tie, if you will. Right? So that's different ways you could be thinking about both in your graph, depending on your research question in particular. So kind of individual attributes like having the same gender, being from the same firm, or these structural attributes like degree, or you could imagine any of the other kind of centrality measures maybe structuring the network. So this is just a hint to the many more measures that you could find about centrality. So of course, reciprocity at the dyad level might be very important depending on your research question. There's a whole series of peer influence measures from Noah Friedkin that kind of drills more into detail about diffusion or influence within a network. Fragmentation, so the key player measures out of Borgatti's UCI net. So thinking about centrality not just as who is important if they could break up the network. So their removal would lead to a fragmentation of the network. And then removal centrality. So what is the effect on the rest of the graph if a particular node is removed? So depending on your research question, you might be more interested in kind of measures in this vein than just thinking about somebody with high degrees or closeness or betweenness. So then thinking about how these different measures might connect particularly to mechanisms for your research question. And one very popular vein in this field is thinking about structural holes and really individuals who are bridging structural holes. So who is connecting people who otherwise would not be connected if the structural hole is kind of the gap in the network that an individual is bridging. So hopefully that sounds very similar to betweenness. That comes a lot out of Ron Burt's work kind of in the structural holes framework where he provides really a lot more I think, theoretical support and components that we'll get to in a second of how you would calculate the power that comes from structural holes or bridging structural holes, right? And this really gets to the idea that there is social capital in a lack of redundancy because that lack of redundancy in ties might lead to a lack of constraint, right? So if your alters all know each other, they might have more power to constrain you if we're thinking about this like in a business negotiation sense. Right? So if you have more power or brokerage, if you don't have that constraint, and if you kind of get to control either information flow between two different groups within the network, or your alters aren't all able to communicate with each other against you. Okay. And that, of course, leads back to Zimmel, if you're coming from kind of the historical sociological tradition or grant a better strength of weak ties, right? All getting at this, the idea that there's this power that comes from kind of being the bridge. And there's a lot of ideas of why that might be the case. So depending on your setting, it might be simply something like negotiation, right, or leverage. It might be that you have better social skills because it's hard to be a bridge between groups. Okay, so there's a lot of different ways you could think about kind of that, again, the conceptual underpinning of why we might care about structural holes or bridging structural holes. And Bert relates this back to 4 network features. So the effective size of an individual's network, right? So thinking about the redundancy or your connections to your alters versus your alters' connections to each other. Efficiency, right? Constraint, again, so the room to kind of exploit those structural holes and negotiate. So that connections between alters, between each other. And hierarchy. Right? So there are a lot of measures for hierarchy in general. For Bert in particular, it would be the extent to which constraint is concentrated in one particular node or actor. Right? So these measures, I think, are important to think about just because if you're in a social science field or connecting to social networks in a social science field, you might hear them come up a lot. You might see a lot of Bert's work in the orgs and business literature. And it's kind of indicating another tradition or another very popular way of thinking about benefiting from network structure, kind of through this mechanism of power. Okay, so if we left our first bullet of centrality behind, moving on to connectivity and cohesion. So I'm going to focus on triads and transitivity, then clustering, and a little bit of structural cohesion, just to give you a heads up for where we're headed. So if this is thinking a little bit more about the patterns of connections between actors. Okay, so the network structure beyond centrality, how might we get to these more kind of structural arrangements and describing our network in a more patterned structural way. So you've probably considered reciprocity at a dyadic level. Transitivity at a triadic level is a little more complex, and typically, depending on your process, it might be a little more interesting if you're thinking about kind of broader arrangements rather than just the mutuality of ties within dyads. So we often characterize the extent to which the triads we observe are random or consistent with what we would expect at random versus what we see from a social pattern. So you can use the triad census, what's sometimes called the U-man distribution, to count up the observed triads of each theoretically possible type. So to skip ahead, this is the triad census if you have directed data. So we've got 18 different ways that 3 actors could be connected, which means there's 36 different positions if you kind of consider, all right, so here you could be this actor, you could be this actor, or that actor, right? So 18 triads in the census, and then 36 positions. And then you can consider the transitivity of those triads. So if I has a tie to J, J has a tie to K, then we'd expect this tie between I and K. Okay. And with directed ties, you might have, there's kind of a lot of jargon and terminology around whether you would observe transitive, intransitive, vacuous triads. So for example, we have a transitive triad here, right? Because this person is nominated both these individuals, they have ties between them. You might observe something like a cycle, which the cycles we observe down here. So person A nominates person B, who nominates C, who nominates A, right? But we don't have that mutuality. It just kind of creates this loop or cycle. So depending on your data, your process, what you're measuring, you might expect you might measure against random, do we have more cycles kind of indicating more hierarchy than we would expect at random? Typically in peer networks, we see a lot more transitivity than expected at random because you tend to know the friend of a friend, right? And you tend to hate the enemy or your enemy's friends, right? Just like you hate your enemies and all of that. You can go on with the friends of a friend and enemy of an enemy stuff. But the point being that you could kind of think about it as this comparing what we observe to random and thinking about transitivity as this indication perhaps of larger patterns in clustering. A slightly larger pattern that typically comes up compared to dyadic or triadic groupings is this small world idea. So what's the probability that 2 nodes would be connected? So this started with Milgram's classic 6 degrees of separation experiment. So if we give a packet to stockbrokers in Nebraska, Kansas, they're going to Boston, but where? they start Kansas or Nebraska? I embarrassingly forget which one of the middle states it is. But anyway, how long would it take to get that to a stockbroker in Boston, right? And he came up with, well, it averages 6, you go through 6 other people together there, so it's 6 degrees of separation, kind of the classic there. And then Duncan Watts has kind of taken on this small world idea about why do we see these small local changes which can have big effects on kind of global network structure? Particularly, we see graphs that have a small average path length, even though they're relatively clustered, right? So we'd expect if we have very high clusters, we wouldn't necessarily have a lot of links between them. So it's a bit counterintuitive, just on the face of it, to think about why we might observe this small world phenomena in social networks so often. Okay? And this brings us to thinking about clustering or clustering coefficients. So you can measure it in 2 ways, thinking about average local density, so your ego network density over the number of nodes, or transitivity ratio. So out of all of our triads, right, how many of them are closed? So how many times would the friend of a friend be a friend? Okay. And we see that these small world graphs occur because there's a lot of power to reduce path length that comes from having shortcuts between clusters in the graph. So having just a few shortcuts between clusters can dramatically reduce average path length. And that's what we typically observe in these social networks or traditional social networks like Milgram had. So you know one person in Kansas who has a cousin in Boston, right? And it's not like we have to go through every state in between. We have this shortcut that kind of connects these separate clusters. So conceptually, these small changes, like shortcuts, could have a big effect on kind of the capacity of something to spread through the network. So that might be very important if you're thinking about something like disease transmission. Okay. And just the heads up that this is just a very small taste of a much broader literature, because thinking about clustering and calculating it can get very complicated. Okay. So thinking about structural cohesion a little more conceptually. So kind of, again, extending beyond, if we've moved from centrality to clustering, now to cohesion, the extent to which the networks or subgroups within networks are cohesive, are held together, interconnected, resistant to disruption, kind of sticky. Okay. This can be very challenging to measure, okay? Yeah, particularly of observable structure. So what is actually holding the group together? So networks can vary in the extent to which the connectedness flows through one or a few actors, right? So do you have a lot of different paths connecting nodes, or is it centralized in one actor? So the more paths you have in your network that don't rely on just one actor for flow, the more cohesive your network would be. So one step towards measuring this is thinking about reachability. And reachability can be a centrality measure for individual nodes, just like closeness or degrees or betweenness. But if you think about reachability as actors I and J being reachable if a path in the network connects them, the more paths that are linking the entire network increases this cohesiveness of the group, the ability of the group to hold together. This is different from density. So here we could have 2 graphs of the same density, but it's really that pattern of the ties. It's the position of that tie that matters, right? That would shift the cohesiveness of our group. So having a cohesive group, right, where nodes can be reached versus not. It's also different from volume. So you can have graphs that have the same volume of ties, right? But the graph over here on the right has many more independent paths that are connecting individuals, right? So we could see that you could go this way to connect these individuals, right? Separate paths leading to a more cohesive network, even though your networks could have the same size, same density. So it really is this structural idea that can't just be reduced to kind of the typical centrality measures of degree or of density. And so this leads to the idea of a component, which we talked about briefly before because it can be useful when you're thinking about things like closeness. But a maximally connected subgraph, right, within your graph, or it could be your entire graph, depending on your data. So a connected graph where there are paths between nodes. And some important terminology you might want to think about or be familiar with is a cut point. So that's the node whose removal would disconnect the graph. So node 4 here, if we took them out, our component would break into 2 pieces. And so in an entire graph, you might have a cut set. You might have a lot of different nodes that are in a position like 4 where their removal would break up components. You also typically see the components referred to as strong or weak, right, depending on if your data is directional or not, or if you're considering directionality. So weak components would ignore that directionality. And if you were thinking about directionality as kind of an important part of your network flow process, then you might want to make a distinction between strong and weak components. Oh, sorry. So that gives us to a formal definition of structural cohesion. And there's really two ways of framing it that are exactly the same. So it would be the, excuse me, the minimum number of actors who, if removed, would disconnect the group, or the minimum number of independent paths linking each pair of actors in the group. There are also a lot of ways you could talk about components, or you might want to relax the definition of components, say. So you could think about K components, where K can take on the value of any number of paths that's linking individuals. So a lot of times you see bicomponents because you're really interested in the kind of a stronger component than people who are just linked by one path. You want the people who could be linked by two paths. So it's a slightly stronger definition. It's a little more sticky cohesiveness, if you will. So thinking about components kind of just on a conceptual or theoretical level, every member must have at least K ties, whether you set K to be 1 or 2 or 7 or whatever, depending on your data. But just because you have K ties doesn't mean you're necessarily in that component or you have a component in your graph. Components can only overlap by K minus 1. So if you're thinking about a bicomponent and you have two members of two separate components and they have two paths linking each other, then they would be in the same component, right? So there's kind of a constraint on your overlap there. And components can be nested within each other, right? So you could have the people who are connected by one path as a component, and then within that, people who are also connected by two independent paths in a bicomponent. And this leads to a measure of embeddedness. So identifying cohesive groups or blocks within a network, and then removing people in the K-cut set successively to see who is more deeply embedded or nested. What are the more deeply embedded groups in a graph? So if we think about, I think I have them, no, I don't have them highlighted. Person 20 here, these lines kind of outline the different levels of embeddedness or nestedness within our graph. So person 20 is a part of this small local component, but then there's connections here between 5 and 21 and 19 and 7, so they're part of this whole left-hand side component here with the dark dashed line, and then of course they're part of the overall component we're observing. So you get kind of this nestedness as you get increasingly embedded within the network. And so you might expect then that there's a higher embeddedness level if you are measuring that for 20, right, compared to 13. And you can consider components for ego networks, right? So you have a lot of different types of substructures within the network. This is another area that gets very jargon heavy very quickly. You might see a lot of these terms, or you might be interested in particular ones depending on what you're measuring. So cliques would be all members, a group of nodes where all members are connected to all other members. You can relax that to be an N clique, where N would be a number of steps it would take. So not just considering your friends perhaps, but your friends of friends. So a two-step, a two-clique. Defined by this kind of two-step of ties, or a friend of friends, and you could imagine going on from there, from two. But with say a two-clique, your friends of friends, that kind of intermediary person might not be connected otherwise in the clique. So a clan would restrict that to only connections that go through other members. So you can't kind of go outside the clan to be connected within the clan. So it's only people who are connected through other members, only considering connections through other members. And then a K-core is another kind of relaxation that is used in a lot of different cases where you're considering members who are joined to at least two other members, even if they're not connected to everyone. So we say, okay, who is our 6 core? Who is connected in this group to 6 other people, even if they're not necessarily all connected to each other, which is the slightly more restrictive definition of a clique. Right? So you can kind of think of different ways of relaxing this idea of how would we measure different subgroups or different substructures. Okay, so then moving on to just the last chunk of what we're going to cover today in descriptive, in our network description section, or network descriptives, thinking about roles and positions. So this is a bit of a shift away from thinking about the patterns of ties, of structures in the broader sense, to kind of, again, slightly different mechanism of why we think those ties and positions might matter. So maybe more positional, less connectionist. Okay. So overall, thinking about roles and positions as measures that are describing subsets of actors or nodes who have similarly structured relations. So we're not interested necessarily in people who are connected to each other, but we're interested in people who have the same types of connections to other individuals. Okay? So we might expect different behaviors, different risks, right, for transmission or for certain behaviors, for actors who are occupying similar positions or roles, even if they're not necessarily connected to each other. So here this is the example kind of family graph that you saw yesterday with Jim, right? So who bickers with whom? If I had ties here, I don't, but who feeds whom, and maybe kind of romantic love. We have parents and children. So we'd expect that kind of parents to be in a similar position, right? Similar roles, and because of that have maybe similar risks. Or we could have something that's a little more hierarchical, so maybe this is like a boss and middle management and employees, something like that. Okay. We could typically characterize this as structural equivalence. So actors are equivalent if they have the same ties to the exact same people in the network. So this is fairly restrictive, and it's very rare that you would see this, okay, in a network. It's maybe more restrictive than you would want to think about roles or positions in a network. So we typically relax this to regular equivalence. So actors are equivalent if they have the ties to the same types of alters, even if it's not the exact same nodes or the exact same people. So conceptually, this is a very general way to think about multiple relation networks, to kind of characterize these multiplex networks. The intuitive example is kinship, right? So in the US, in English, you have a cousin, a first cousin. It doesn't matter if that's your mother's sister's son or your father's sister's daughter or whatever, it's your cousin, because we're defining that kind of role, regardless if those individuals are connected to the same people, right? So if you have cousins on two opposite sides of your family, they were both your cousin, but they're not necessarily related to the exact same individuals, okay? So kinship is kind of a good conceptual example of where we're doing that by default. We're referencing regular equivalence just in our terminology, at least in English and in the US. And this is kind of a conceptually untapped way, I would say, or really Jim would say, of thinking about these kind of characterizing multiple relation networks. So there's a lot that needs to be done and could be done thinking more about equivalence and about kind of these structurally equivalent positions. So just to walk through our example here, we would see that C and D and then E and F have structurally equivalent positions. So they're connected to the exact same people, right? So C is connected to A, and then G through J. D has the exact same patterns of connections. Okay? Same with E and F. And then G through J and K through N are also structurally equivalent, so they have the exact same connections as each other. If we think about regular equivalence, A and B are in regularly equivalent possessions, so they're not connected to the same people. B is not connected to C or D, right, like A is, but they both have connections to people with the exact same patterns of ties, right? So the connections to C and D and the connections to E and F are structurally equivalent based on the patterns of ties of nodes C and D and E and F. And you'd see the same thing with regular equivalence from C through F. So they're in the same regularly equivalent position, and then G through N. So practically, if you're thinking again about kind of bosses and middle management and employees. Yeah, sorry. Yeah. I don't know, do they? Yes, there you go, yes. So one of the only examples, speaking of untapped potential, that I could kind of dredge up with minimal research, I would say, or discovery, is from Fujimoto and Valente, when they're looking at adolescents' exposure to drinking and smoking based on structural equivalence and network cohesion. And they actually find that your exposure in these kind of structurally equivalent positions is a better predictor of your smoking and drinking behavior than your connections to individual peers, right? And if we think about this, it might be the kids who are connected to the very popular students who are at higher risk for drinking, right? And it doesn't matter necessarily who those very popular students are. If you're connected to students with a lot of other connections, you might have a greater risk for drinking or smoking, right? So this is kind of a proof of concept of the structural equivalence. Their paper gets a lot more complicated because of this kind of exposure aspect, but it provides like at least a practical way, hopefully, to grasp onto what structural and regular equivalence could mean and why you might think it would matter for a network and kind of this role and position framework. Okay, so in summary, I think I'm going to finish on time, and I'm very proud of that. I hope it hasn't been too fast. There are a lot of ways that you could be describing networks. We are really only scratching the surface here, and hopefully it's providing kind of this urge to think about the different ways you could characterize the patterns of ties more conceptually so that you're then able to find the appropriate measure for your data and really for your research question of interest. So here we've looked at individual properties of nodes, particularly in terms of centrality, and then entire network counterparts. Within that, most of those also applying to ego networks as well as sociocentric data, and then thinking about structures and subgroups. So centrality, connectivity, and cohesion, and then roles. Again, you could kind of frame this as this micro, meso, macro process, depending on your data, your research question. Are you really interested in the micro processes connections between individuals? Are you thinking about subgroups and clustering, or are you thinking kind of on a macro level, what is the density or the transmission potential in my network? Oh, I'm just kind of reiterating that. So just to point out some of the ways that this is not mentioning things that you might want to be considering in your research question and in your data. So we're only thinking about stable networks here, right? So this isn't in any way considering any kind of dynamic process in the networks or effects of changes, stability and churn over time. It also is only looking at one mode networks. So if you have bipartite networks, there are certain measures which will not be appropriate and other measures that might be more appropriate. So that would be kind of a separate vein of literature than what's been covered here just for the sake of time and kind of for what is more typically just what we expect people to have as kind of their typical data. And there are a lot of kind of challenging additions and ways to move forward from here as well in terms of descriptive. So block modeling, which you'll get a little bit from in the next talk, and then centrality or structural measures that might be specific to certain topics or processes. So again, just to urge you to think about these things very conceptually in terms of what makes sense for exactly what you're talking about in your network, for what constraints are imposed by your method of data collection, and the ways that you really want to have kind of this theoretical underpinning for whatever measure you have used in a way that explains it appropriately in terms of your research question. Any questions? Great, thank you so much.